Hello, this video is about explaining the concept of criticality-based ray event simulation. It has been produced by OFFIS in the context of the ITF3 Testomat project, which deals with the next level of software test automation. First, let us quickly introduce OFFIS in a nutshell. We are a non-profit research institute for information technology that is located in Oldenburg, which is in the beautiful north of Germany. About 300 employees are working towards our objective to transfer scientific knowledge into industry. If you want to learn more about OFFIS in the Testomat project, follow the link in the video description. What is the motivation for criticality-based ray event simulation? First of all, we are speaking about reliability engineering and more precisely about the safety assessment of so-called safety-critical systems. In this context, our main goal is to build systems that operate sufficiently safe and, at the same time, to prevent accidents, which are quite rare in general. For this, we have to ensure that the system under test, or SUT for short, shows no critical behavior at all, or at least only with a bounded probability. That is, with a probability that is guaranteed to be lower than a given specific and generally accepted threshold. Here we have to face several challenges. Firstly, safety-critical systems are often too complex to check through every possible input combination or to conduct analytical model checking, if ever, or even to test them manually. Our approach to overcome this is to do simulation-based statistical model checking. That means we test the SUT by simulating it and then by inferring statistically whether the samples give evidence that the system complies with some prescribed requirements. The second challenge here is the fact that critical behavior of well-engineered systems tends to be extremely rare, that is, speaking of probabilities of order 10 to the power of -6 or even less. Now, if we sample simulation runs for the system simply in a random fashion by so-called pure Monte Carlo, we would have to spend a huge amount of simulations in order to achieve good estimates of the critical event probability. So, our approach to this is to apply criticality-based ray event simulation. By this we mean a number of intelligent simulation strategies that aim to guide the system under test into rare critical states. They do this by maximizing an objective function modeled for a given system. We call this criticality function. To apply the methodology, we assume several things to be given. First, the system under test and the environment in which it is intended to function. This should be given as executable simulation model and can be a black box, for which we only know the inputs and the outputs, but not how it works. Further, we assume that we are given some requirements that the SUT should comply with. These can be, for example, safety requirements. From this, we then derive a specific criticality function for the system. This is done by following the idea that the more the requirements are harmed, the higher should be the criticality. Now, let's have a look at how it works. Again, we consider the SUT and its inputs and outputs. That is what we simulate for a limited time frame, and we execute simulation runs. The criticality monitor obtains the simulation outputs and computes the criticality for the simulation run according to the criticality function. Then it passes the criticality values to a component that we call Ray Event Simulation Test Manager. This component has a variety of algorithms from the domain of ray event simulation implemented, which all aim to maximize the criticality for the system. We will come back to this in a minute. Based on the idea to maximize the criticality, the test manager computes the input values for the respective next simulation run. Now, what types of approaches can be used for our purposes? A rather standard approach for ray event simulation is importance splitting. Here, the idea is to reset the simulation along the trace, namely to earlier points in time that seem promising to reach a critical event. You can grasp this idea from the picture on the right. Importance splitting can be applied whenever the test system comprises time-dependent stochastic decisions, for instance, if they are probabilistic. The reset algorithm, introduced in 1991, is one of the common techniques for importance splitting. In the course of the Testomat project, we from OFFIS also developed some own ideas regarding importance splitting. Another quite traditional approach for ray event simulation is that of importance sampling. Here, the crucial idea is to modify probability distributions in such a way that the frequency of ray events gets increased during the sampling process. As long as the modified probability distribution is chosen adequately, we can expect the estimate of the critical event probability to be much more precise compared to pure Monte Carlo. Importance sampling is applicable when the test space is parametric and the underlying probability distribution is known. Of course, this works as well if there is no distribution attached to the test space, because in this case we can assume a uniform distribution on the parameter space. In the course of Testomat, we studied the TUTS algorithm by Puch and others, where TUTS stands for Threshold Uncertainty Tree Search. TUTS is based on importance sampling and aims at finding rare critical events by learning iteratively from previous samples. A new approach that OFFIS could develop in the course of the project is to use optimistic global optimization for criticality-based ray event simulation. The crucial idea is to use the function evaluations and some rather weak assumptions on the criticality function to estimate upper bounds of the criticality on subregions of the parameter space X. This is why the approach is called optimistic. We can see a graphical depiction of the subregion splitting idea here on the right-hand side. In general, optimistic optimization can be applied for any test space that is a bounded, real-valued, and time-independent parameter space. To name some examples, we can use algorithms such as WHO, POO, DO, or its generalized version SU, or the HCT or the PCT. You may look them up in the publications that we state here. So, what's next? Thanks to the Testomat project, we could apply criticality-based ray event simulation on an industrial use case. If you're excited to learn more on this, please watch our second video, Criticality-Based Ray Event Simulation Application. The references we used in the video are given here. Thanks for watching, and please don't forget to subscribe.